Bismillahirrahmanirrahim. Okay, inshallah, today we will talk about possibly one of the most important topics in Algebra 2 or in mathematics in general, because you kind of use this almost every day in real life. Okay? And this is about standard deviation. And it's very important to understand this topic with a reasonable degree of confidence. You cannot interpret your SAT scores, ACT scores, or read any journal article, scientific journal article of any repute without understanding these concepts. Okay? So it's very, very important to understand this concept of standard deviation. Okay? So let's say you have exams, right? So, and your teacher comes and tells you, it's really upset. It says the average score in the class was 60%. Right? The teacher is really, really upset. It says average score in the class was 60%. Now, if you're like me, you're saying, I hope I'm on the other side of the 60%, right? You hope that you brought the curve up and not down, right? So, but look, okay? But look, let's say there are 10 students in this class, okay? Look, I'm going to give you some scores, okay? So these were the scores. 22 out of 100. The percentages, 54, 56, 58, 60, there were two 60s, and then 64, and 66, and 68, and there was one superstar, there's always one, right? It's 92. So the average of this is 60, all right? So this was like, the average was like 60, okay, right here. You follow? But, okay, but let's say if your teacher had walked in this class, average score in the class was 60. Okay? And then they say these were the scores. 0, 0, 18, 50, 80, 82, 88, 92, 94, 96. Different. But if you don't believe me, see, the average of these two numbers sequences is the same. So here it is. Look, the first set of numbers I gave you, 22, 54, 56, 58, 60, 60, 64, 66, 68, 92. All of their 10 score divided by 10, 60. The second set of numbers I gave you, 0, 0, 18, 50, 80, 82, 92, 94, 96, 88, and divided by 10, average score 60. These two kids were sick. What do you think about that? Okay. Not bad, huh? So, but then you got fooled though. There's a problem here. The average score here was 60%. The average score here was also 60%. But the data set is very different, right? You agree? Yeah. So, in other words, when we say average, we mean mean, right? Okay? So, different statistics books give different symbols for mean. Sometimes it's this. Sometimes it's this. This is mu. Mu. Okay, I'll tell you how to remember that. I got one for you. So, that's like okay, so mu is sometimes a symbol for mean. So, but anyways, whether you use this symbol or this symbol, that's like, fancy symbol for mean or average. So, in other words, average is, okay, you got, 60% average, right? You have a certain concept of 60%, but you got fooled, right? So, it is not sufficient to give an understanding of the data, correct? It's better than nothing, right? So the average score was 60 could mean something like this, or Would you rather be in this? I hope you're in this class, right? So now there must be something else. There must be some other way of describing this set of data, other than just mean, to give us a better picture of the data, correct? Okay, so let's say teacher comes into the room and you don't know this data yet, okay? And the teacher says, okay, the average score was 60%. Okay, and then the student raises his hand, this smart student. Okay, teacher, I hope it kind of was like, my score was kind of like far from the mean, on the higher side. Yeah? So he's hoping where? If the average was 60, he's hoping he was very far from the mean. So he says, okay, and the teacher goes, Shabash, good job. Don't worry, Ahmad. Your score was very good, very good. You were far from the mean. And this other kid goes, oh, I got an idea. And the second kid raises the hand. Oh, teacher, I hope I was kind of far from the mean too. And he says, no, you are not. You're far from the mean. You could be a little farther. It'd be nicer for you. And then the kid goes, teacher, I was sick. He says, that is not an answer. But look, this concept of being far from the mean is important to the student, wouldn't you say? Every student's got the idea now. Okay, I want to know how far away I was from the mean. Yes? Because the farther away you're from mean, this way, on the good side of the teacher's happiness circle, you know what I'm saying, the better you off. Do you understand? See, that's what standard deviation is. If you just listen to the terms, standard deviation. Deviation means what? How far away you are. So somebody could be far deviated to the mean towards the 100 side, or somebody could be far deviated to mean to the 0 side. The standard deviation means the average of all the differences from the mean. Does that make sense? So if you look at this data, the first set of data is kind of cluttered in the middle, right? So if I were to redraw this data, let's say if I just kind of pictorially represent it, the first set of data was kind of like in the middle, right? Correct? And the second set of data, okay, it was kind of like over here, and most of the kids are over here, right? Do you follow? So, but the mean for both of them was here, correct? So, standard deviation, or this, okay, is just a measure of how far each individual point is from the mean in either direction. Does that make sense? So, in the data like this, now if it's just an average, the smaller the standard deviation, the closer the data is. The bigger the standard deviation, the farther spread the data is, correct? Does that make sense? So standard deviation is a measure of spread of the data, how the data is spread. Another word, a way of saying the same thing is dispersion. Dispersion is how dispersed the data is, correct? So mean or average is only one way of getting the big picture of the data. Another way of getting the big picture of data is standard deviation, how far away from the mean the data is. So a simplistic definition of standard deviation is how far away from each data point is from the mean. Does that make sense? Okay. Now, how do you calculate it? Now, it's a nice concept, genius. So how do we calculate, you say? Okay? Well, we have to give the data points names. Okay, let's call, now these are 10 students. So you take x, let's call these data point x1, x2, x3, x4, to x9 and x10, correct? Okay, you follow? You got that, right? So that's just individual data point, correct? And then you can calculate the mean of this, and you can call the mean x bar, or you can call it mu. Okay, your book calls it mu, so we might as well call it mu. It's kind of cute anyways, right? So it's kind of mu. What's the mu? All right, what's mu? What's the mu with you? No. So it's mu r this, okay? So let's say you do all the x's. So now, first of all, understand what x bar is. X bar or mu is just what? x1 plus x2 plus x3 all the way up to x10 divided by, however, in this case, it's 10 x's, correct? Okay. Now let's talk about in generic terms. Let's say you don't know how many students there are. Let's call it n number of students. Is that fair? So this is x1, x2, x3, and dot, 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 all the way up to xn, however many students are. So the mean would be, okay, x1 plus x2 plus x3, dot, 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 all the way to xn divided by n, the number of x's there are, correct? Does that make sense? That's fair enough, right? Okay, now, how do we calculate the average distance though? Okay, now let's see if we do this, okay? Let me make this line, and let me put here, over here, let's say that's the mean, x bar or mu, okay? And let's say here are the data points, okay? So we'll call this x1, x2, x3, dot, 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 x, blah, 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 all the way to xn, correct? Correct? Okay, now, look what we want to calculate. We want to calculate the average distance from the mean. So, what we have to do is we have to, okay, let's say, we have to take x1, right? And subtract from it x, the mean. So, we take x1 and subtract from it the mean. Should I use mu or x bar? What do you guys say? Mu. Okay, subtract it from the mean. Okay, I got that one. And then I'm going to have to do x2 and subtract the mean, right? And I have to take x3 and subtract the mean, all the way up to xn and subtract the mean, right? You got this? And I divide this, if I divide this by, no, we don't have 10, we have n now, right? I have n number of data points. Divide this by n, I will get the average distance from the mean, right? Right?
So you have to add all the data?
Yes, in each individual data points, wait, we're not done yet. Look, each individual data points and subtract the average or from how far they are from, right? You follow? And then divide by the, there's a problem with this. Problem. Okay? What's the problem? Okay, let's say this is 60, and let's say this is 20. So 20 minus 60 is what is this? Negative 40. Okay? Let's say this point here is 80. Okay? 80 minus 60 is? 20. Last time I said. Do you understand? So all of these data points will be, over here, negative differences, right? Correct? And all of these data points will be positive differences, right? Right?
Yeah.
And mean is right in the middle of it. So all the negative differences and all the positive differences will add up to equal exactly opposites. And they all cancel each other out. So, do you understand? So if you...
It's what the absolute values are, right?
But if you put the absolute value, do you understand? But first you have to understand how these will cancel each other out. Because if you do x minus mu over here, all these are negative numbers. And then on this side, it's all positive numbers. Okay, and this is the mean, it's right in the middle. Okay, let's say these add up to negative 600, and these add up to positive 600. You add them together, numerator will always be 0. That's what happens if you subtract from the mean. Do you follow? So this does not work. So you have to take, let's say you have to take absolute value. You want the absolute value, just the distance from the mean, correct? Because remember, that's the definition of absolute value. How many times have I hammered that in here, right? Absolute value is the distance from 0. In this case, absolute value is the distance from the mean. So we have to do this something super duper, like massively important thing over here. And this massively important thing is, we have to take absolute value of every single one of these. Correct? You get it? And this will be standard deviation. We gives this symbol. This is lowercase sigma. You know, uppercase sigma is this, which we know. This is lowercase sigma.
So it's the absolute value of E.
Okay, I'm going to rewrite this. Watch. So, standard deviation. Okay, very important. Is the average distance from the mean. You call this sigma, lowercase sigma. Okay, that's what that is. Or you can just sometimes just write standard deviation like that. All right, is this. Okay, now that's going to be. Just watch this. It's going to be all the differences from the mean taken absolute value. So x1 minus the mean plus x2 minus the mean plus x3 minus the mean. Absolute value of all of that because you don't want the negatives canceling out the positive. All the way to x to the n minus the mean, right? And divided by total number of n's. Okay?
So it's the absolute value of the quantity of x1 minus
mu, correct.
Absolute value of x1.
Correct. Yes, it's the you just get the difference and just make it positive, right?
Okay.
So this is like absolute. This is perfect standard deviation. That's all it is. Okay, but this is not the standard deviation formula that you use in statistics, because the problem is you don't. It's apparently, all right. I'm not a statistician, right? I'm not a math person, right? But so apparently, the absolute values in the computer world and the mathematics are not easy to work with, okay? So, this would work perfect if the math was easy, okay? So, we don't want, how else can you describe the same thing? If you understand this, you understand standard deviation, okay? But how else can you describe the same equation, but indifferently in mathematics, okay? Now, look what we're doing over here, okay? Look what we're doing. What we're doing here is taking something that we're just making sure it's positive, right? Make sure it's positive. Note to self, make sure it's positive. Note to self, make sure it's positive. That's all we're doing, right? Is there another way of making things positive other than absolute value? Squaring them. But if you square a number, you change its value, right? And then you square, yeah. So what you can do is you can take -3, and then you square it, and you take the square root of that. What'd you get? -3 squared is 9, that's 3. You made it positive, right? So if you square something, and then you take the square root of that, you make it positive. That's a pretty nifty trick. Okay, so that's good. That will work. Okay, so we'll do this, okay? All right, so we do this. So, okay, we take x1 minus mu, and then you square it, and then you take and then you right away take the square root of that. And then you do the next one. You take x2 minus mu, and then you square it and take the square root of that, plus, and then, same thing, x3 minus mu, and then square that, take the square root of that, and then all the way into the n. You take x to the n minus mu, and then you square that. I want to make sure it's a perfect square. Okay, make sure, and then take the square of that. Got it?
So do you do one or the other, or can you?
No. I'm going to summarize it for you in the end. We're in the process. Okay? Now look, you did this, right? Now, both of these do the same thing. You agree?
Yeah.
Both of these do the same thing. Okay. All right. Phew. But this is kind of cumbersome. Kind of cumbersome. So what you do instead is this. Now, this is exact standard deviation. But if you do this, you get almost the same answer. Okay? If you do this. Okay, wait, just try to make it this neat, okay? If you do this, you get almost the same answer, okay? You take x1 minus the mean, you square that, plus x2 minus the mean, and you square that, plus x3 minus the mean, you square that, plus ... and you take x to the n minus the mean, and then you square that, and then you do all the squares and you add them up, and then after you divide by n, then you take the square root of the whole thing. This ends up being numerically about the same, but it's more precise to say this. You agree?
Yeah.
This is a little fudge math, okay? But this is standard deviation. Okay, you get it? Okay, so far so good. Now, this is kind of clunky formula. So I'm going to just rewrite this, okay? Sigma, okay? Okay, is, I'm going to do this, x1 minus mu. You have to understand this thing one time, and then once you understand it one time, it's good for life, inshallah. So it's worth the patience to try to do this. Xn minus the mean squared. And then divide this by n. You agree? Okay. Now I'm going to rewrite this, okay? Excuse me. I'm going to rewrite it as this. Ta-da. Because this is just a sigma notation, that's probably why you use standard deviation for this little baby sigma. Now this is just, if you expand this, you get that. Do you understand? What this is saying is this, okay? Expand this series from I equals 1 to however many there are of x to the I minus the mu, and then square it. Now if you expand this, you start with 1, right? X to the 1 minus mu square, and then expand then x to the 2 minus mu square, dot, 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 all the way to the x to the n minus mu square, right? So, and then I all the way up to 1 to n. Do you understand?
Yeah.
So this is a simplified way of writing this whole series. And this is the formula for standard deviation. Looks complicated, but if you take it piece by piece, that's what it is. So let me rewrite just the formula, and I just want to suggest a couple. So this is standard deviation. The formula looks complicated, but it's not. It is a sigma notation. I equals 1 to n from x sub I minus mu, and then square it, and you take this whole thing and you divide it by the number of n, and then you take the square root of that, then you get standard deviation. So in the data set that we first gave, the really smart student in the first case scenario got like the 96 or whatever, he says, he raises his hand, says, but teacher, what was the standard deviation? You understand? Then they would know a lot more about the data. If the standard deviation was small, that he would be afraid. If the standard deviation is a large number, that means the data is more scattered. Right? Does that make sense? So look what you need. Look at the components of standard deviation. Okay, this formula. This is just individual data points. So that is, okay, so x sub I is data points, right? Data points or data values. Let's call it data values, right? Okay? This is the mean. Okay? N is the number of data points, data values. Okay? And lowercase sigma is the standard deviation. And if you understand this, alhamdulillah rabbil alameen, this is indeed one of the most important concepts that we will study, and that's standard deviation. Inshallah, after a short break, we will elaborate on this concept, inshallah. I is just a number for sigma notation. Remember, sigma notation is, this is the start. You could have used anything. I could have used r over here. R equals 1 to n. Maybe that would have been interesting.
Yeah, I was a little like,
Should we use r?
Yeah, because
You can use I instead of I. You can use, this is what your book uses. I use that. So you can use R, whatever it is, you know, from 1 to whatever. Maybe next time I'll do R. You can write it like this. See, r equals 1 to n. Maybe I'll do that next time. X sub r minus mu, square root of all of that, and then divide it by the number of n. And then take square root of all of this, and this will be standard deviation formula. Does that make sense? Inshallah. So we'll take a brief pause until the next time. Assalamu alaikum.